A support vector machine, SVM, is a supervised machine learning algorithm used for classification and regression tasks. It works by finding the optimal hyperplane that separates data points of different classes with the maximum margin. SVMs are effective in high-dimensional spaces and can use kernel functions to handle nonlinear data by implicitly mapping inputs into higher-dimensional feature spaces. They are widely used for their accuracy and ability to model complex relationships in data. Introduction. SVM. A support vector machine, SVM, is a discriminative classifier which intakes training data, supervised learning. The algorithm outputs an optimal hyperplane which categorizes new example. What could be drawn to classify the black dots from blue squares? A line drawn between these data points classify the black dots and blue squares. Linearly separable data. Linear versus nonlinear separable data. What could be drawn to classify these data points, red dots from blue stars? Nonlinearly separable data. Here, the hyperplane is a 2D plane drawn parallel to x-axis, that is the separator. Nonlinearly separable data. Nonlinear data, type 2, raw data line as hyperplane. For the previous data, the line, if used as a hyperplane, two black dots also fall in category of blue squares. Data separation is not perfect. It tolerates some outliers in the classification. This type of separator best provides the classification. But it is quite difficult to train a model like this. This is termed as regularization parameter. Tuning parameters. SVM1. Kernel 2. Regularization 3. Gamma 4. Margin. Margin is the perpendicular distance between the closest data points and the hyperplane. On both sides, the best optimized line, hyperplane, with maximum margin is termed as margin maximal hyperplane. The closest points where the margin distance is calculated are considered as the support vectors. Regularization, also the C parameter in Python's sklearn library, optimizes SVM classifier to avoid misclassifying the data. C large, margin of hyperplane small, C small, margin of hyperplane large, misclassification, possible, 1. C large, chance of overfit 2. C small, chance of underfitting. Gamma defines how far influences the calculation of a plausible line of separation. Low gamma points far from plausible line are considered for calculation. High gamma points close to plausible line are considered for calculation. High gamma value, low gamma value. Kernels, mathematical functions for transforming data using some linear algebra. Different SVM algorithms use different types of kernel functions. Kernels, mathematical functions for transforming data using some linear algebra. Different SVM algorithms use different types of kernel functions. Example, k, x, y, equals f, x, f, y, kernel function dot product of n-dimensional inputs. The kernel function, x, y, equals, x, y. K, x, y, equals f, x, f, y, computes the dot product of the mapped inputs x and y in an n-dimensional feature space. This allows for efficient similarity measurements and enables the creation of nonlinear decision boundaries in models like SVMs without explicitly mapping the inputs to the high-dimensional space. In this example, the kernel function, x, y, sadface x, y, 2k, x, y, sadface x, y, 2, maps the input vectors x sadface x1, x2, x3, x sadface x1, x2, x3, and y sadface y1, y2, y3, y sadface y1, y2, y3, to higher dimensional feature spaces. F, x, and f, y. The dot product f, x, f, y, in this higher dimensional space results in the same value as x, y, 2 in the original space. For x sadface 1, 2, 3, and y sadface 4, 5, 6, both the direct computation in the feature space and the kernel trick give k, x, y, equals 1024, showing that the kernel function efficiently captures the similarity in the higher dimensional space without explicitly computing it. Pros: It works really well with clear margin of separation. It is effective in high-dimensional spaces. It is effective in cases where number of dimensions is greater than the number of samples. It uses a subset of training points in the decision function, called support vectors, so it is also memory efficient. Cons: it doesn't perform well when we have large data set because the required training time is higher. It also doesn't perform very well when the data set has more noise, i.e. target classes are overlapping. SVM doesn't directly provide probability estimates. These are calculated using an expensive 5-fold cross-validation. It is related SVC method of Python scikit-learn library. Applications: 1. Face detection. 2. Text and hypertext categorization. 3. Classification of images. 4. Bioinformatics. 5. Handwriting recognition. 6. Protein fold and remote homology detection. 7. Generalized predictive control, GPC. This code visualizes the decision boundaries of different support vector machine, SVM, classifiers applied to the iris dataset. The iris dataset is loaded and only the first 2 features are used for simplicity. For SVM models are trained, SVC with a linear kernel. Linear SVC, another linear kernel. SVC with a radial basis function, RBF, kernel. SVC with a polynomial kernel of degree 3. For each model, the decision boundary is plotted, showing how the classifier separates the classes in the feature space. The scatter plot of the data points is overlaid on the decision boundary, with points colored according to their class. Here's a brief explanation of the key steps in the code. Data preparation. The iris dataset is loaded. Only the first 2 features of the dataset are selected for training to allow for easy 2D visualization. Model training. For different SVM models are trained using the selected features and target labels. Visualization. A 2x2 grid of subplots is created, where each subplot corresponds to one of the trained models. The decision boundary of each classifier is plotted using the decision boundary display from _estimator method. The scatter plot of the actual data points is overlaid on the decision boundary for comparison. Display. The plot is displayed using plt.show. If you run this code, you will see 4 plots, each showing the decision boundary for a different SVM classifier on the iris dataset. The differences in decision boundaries will highlight how each kernel function separates the classes in the dataset.